Hello and welcome to this first part of the section 8.3 notes. In this video, we're going to cover the first two pages of section 8.3 notes, so page 60 and 61. Okay, so in this video, we're going to learn the integral test. We'll learn the comparison test in a different video. And so here's the key idea. And we're going to illustrate it with an example, the sum of 1 over n squared. We don't know if this converges or diverges. If it's just 1 over n and I take the sum of that, with that we know it diverges. But the sum of 1 over n squared we actually don't know. But let's try to figure it out. So here's what we're going to do. I tried my best to draw the graph of 1 over x squared, really, right? And now I have these little marks marked off here. Where the corresponding 1 over n squared value is. So when n is 1, I get 1. The scale is kind of crazy, but just bear with me, right? When n is 2, I get 1/4, so there's that point right there. N is 3, okay? Well, if you think about it, 1 over 1 squared is really the area of a rectangle where the height is 1 and the width is 1. So the height of the function is going to provide the height of the rectangle, and the width of this interval 0 to 1 is going to provide the width, right? So this blue rectangle I just drew has area 1 over 1 squared, i.e. 1, right? Because its height is 1 and its width is 1. Now this blue rectangle here, this one has area 1/4, right? Because its height is 1/4 and its width is still 1. Notice just this rectangle here. Now this one here has area 1 over 3 squared, i.e. 1/9, right? This one here has area 1 over 4 squared, so 1/16, and so on and so forth. And so let's observe something here. We see that if I start my sum at 2, then that is less than the area under this function, right? Now, this one we'll account for later, this tall rectangle here. But every rectangle starting with the second one is under the graph of 1 over x squared. And so starting with n equals 2, that's less than the integral from 1 to infinity of 1 over x squared, right? And the picture kind of shows you that. Here's the graph of 1 over x squared sitting above each of these rectangles. And so adding up the area of all those rectangles, which is this, is less than adding up the area under the curve, which as we know is an improper integral. Okay, well, does this converge or diverge? This integral here converges. It's a p integral with p equal to 2, right? Which is bigger than 1. That's all it takes, is bigger than 1. And so now the sum n equals 1 to infinity of 1 over n squared, well, that's just 1 plus, it's this extra rectangle plus all of the other ones. Sum n equals 2 to infinity of 1 over n squared. And now, because this sum from n equals 2 to infinity is less than a convergent value, we conclude that it's convergent, and adding 1 does not change that. So this converges. And essentially what we're using is something called the integral test. So because what we've done is we've managed to compare this series to an improper integral which we know converges, more or less. That's what's going on. But from now on, anytime you see the sum of 1 over n squared, you can just say it converges because it's what's known as a p series with p equal to 2, right? And so for the same reason that the p integral converges, the p series will also converge, and that's by the integral test. So let's come down here. I tried to keep the scale roughly the same, and now you see that this one is taking its sweet time, tending off to, like, the graph of 1 over square root of x is taking its sweet time, pinching off to 0. Eventually it'll do that. It'll get smaller and smaller as we go off to the right, just like 1 over n squared. But you see there's way more room under there than this one. Maybe there's something to that. Let's build some rectangles. So notice 1 over square root of 1 is actually the area of this blue rectangle that I'm drawing, right? Because it has a width of 1 and a height of also 1, right? This blue rectangle here has an area of, you guessed it, 1 over square root of 2. Notice its width is still 1, but its height is 1 over root 2. This rectangle here has an area of 1 over square root 3. This one here, an area of 1 over square root of 4, also known as 1/2, right? And so on and so forth. And so the key observation here is that the area of all these rectangles is bigger than the area under this curve. So the sum n equals 1 to infinity, 1 over square root n, is bigger than the integral from 1 to infinity, 1 over the square root of x, right? Well, this right here is equal to the integral 1 to infinity, 1 over x to the 1/2. Oh, but this is a p integral with p equal to 1/2, which is less than or equal to 1. So this diverges. And so this sum here, this infinite series, is bigger than a divergent integral, and so it must also diverge. The key observation here is that now what we're going to call this is a now p series with p equal to 1/2, right? And so therefore, for the same reason that the integral diverges, the p series also diverges by the integral test. And so anytime you see a p series, you don't have to cite the integral test. You can just say it's a p series, right? All right. So coming to the next page, here we formally define the integral test. It essentially says that if you can integrate, like if you can change the sum to an integral symbol and integrate the corresponding function and get something finite, then the sum must be finite, and vice versa, right? And now your sum does not need to start at 1. It can start at any positive number if you like. And usually it's you start it at a number so as to avoid dividing by 0, right? So like I don't want to start this at like 1, 2, or 3 because eventually I would hit 3 and I would have a 1 over 0, right? So I'm going to start it with n equals 4, okay? So let's look at this integral. It's the corresponding integral and see what we get. So we'll do that here. Integral 4 to infinity, 1 over x minus 3 squared dx. Well, I encourage you to do this by pausing the video and working this out on your own. So what we'll do is we'll take a break here and just find the antiderivative. Well, I need u equal x minus 3 du is just dx. So this is integral u to the minus 2 du, which is minus 1 over u, the antiderivative. And so then this integral here is the limit t goes to infinity. Now if u is x minus 3, that's minus 1 over x minus 3. So I get minus 1 over x minus 3 from 4 to t. Okay, well, this does not depend on t at all, and notice you just get a positive 1, and as t becomes large, you get minus 1 over large numbers, which goes to 0. And so because the integral converges, the infinite series converges. Its value is not 1. That's the value of the integral, right? But because this integral converges, this sum converges. Now, they often have different values. So this converges by integral test. But like I said, its value is not 1. Okay? All we know is that it converges. So that's a fact you're going to be seeing moving forward here, is that often we'll just, like, unless it's a very particular series, like a geometric or a telescoping or something like that, we're going to be more concerned with whether or not the series converges and less concerned about if it, like what its actual value is. There's only very few series you know the actual value of, which is kind of interesting. But let's come to this one now. Let's check to see if this infinite series converges or diverges by checking its corresponding integral. So here we are starting with n equals 1, so we'll start with x equals 1, ln x over x dx. This is the limit t goes to infinity, integral 1 to t, ln x over x dx. Now let's take a break and instead just do the antiderivative. Well, we're going to put u equal to ln x, du is just 1 over x dx. I'll let you verify that really this just works out to be the integral of u du, which is u squared over 2, which is ln x squared over 2. And so I get limit, this integral here, sorry, this improper integral is just the limit as t goes to infinity, ln x squared over 2 from 1 to t. And so this is limit t goes to infinity, ln t squared over 2 minus ln of 1 squared over 2. ln of 1 is 0, so that's gone. And as t becomes large, ln of t gets large towards positive infinity. Squaring that makes it even bigger. So this is infinity, so divergent. So because this integral here diverges, this infinite series diverges, which I'll write as dvgs, by the integral test. And so write your conclusion and then write your reasoning, right? So in this case, divergent by the integral test, and then showing the work showing that you get a divergent integral. Same above, we showed the work that we got a convergent integral, so the series converges by the integral test. Okay, so here, look, I mean, the corresponding integral here, and I kind of already gave it away a couple minutes ago, but like this we've already worked with before, and we know that as long as p is greater than 1, we get convergent, so I'll just write CVGS, and if p is less than or equal to 1, we get DVGS, diverges, right? And so these we can actually just call p series with p equal to either something bigger than 1 or less than or equal to 1. So an important remark here, the harmonic series are very helpful and useful counterexample. Notice that by the integral test, this diverges because p is equal to 1, right? This is 1 over n to the first. So this is another reason why it diverges. Okay, so what do we think about this one? Well, we don't need to even work it out. We see that this is a p series with p equal to 3, so it converges. What about this one? P series p equal to 1/3, so it diverges, right? So on the homework, you'll see you may have 1 or 2 problems where you're asked to use the integral test to determine if an infinite series converges or diverges. They'll be more like this, a little more involved integrals like these two. But this is the process that we're looking for, something like this, right? Like compute the improper integral. It's the corresponding improper integral. If it converges, the infinite series converges, diverges, and the infinite series diverges. All right, so that's it for this video on the integral test. In the next video, we'll get into the comparison tests.